So now we're going to talk about capacitors. You've already seen some of the properties of capacitors in the simulation lab. And so as a very, very basic picture, a capacitor is two separated conductors. We are most of the time only going to talk about parallel plates for a capacitor. But if I hook up a battery to these two plates, this battery has voltage delta V. You know that this is maybe you don't remember, this is the positive side, this is the negative side. So electrons are what move? Electrons are pushed out of the negative side and they build up here. Well, the battery stays neutral. So an electron is attracted from the top plate to the positive to then be pushed out. So that means this misses an electron. So it has a positive charge. So the next electron that's transferred and the next electron that's transferred, we always have an equal amount of charge in the two places. So we're going to say when this is fully charged, this has a charge of plus positive Q, and this one has a charge of minus Q. So there is a new term called capacitance, defined, or we use the symbol C, and it is defined as, I'm using a three-part equal sign because that means it defined. So we define capacitance as the amount of charge stored on the positive plate divided by the battery voltage, the battery potential difference that we had to use to move that charge into place. So this is a definition, and it's very, very similar to, for resistors, resistance was defined as potential difference divided by current flow. So we've defined capacitance, and now we want to know, well, what affects how much charge we get out of a particular battery. So when we build a capacitor, there are several things that go into play. First of all, the area of these plates. The bigger the area, the more charge that can be stored because there's more room for them to spread out. Like eventually, charges stop moving because this is full. There is a repulsion to any more electrons coming because of all the electrons that exist here. So we reach an equilibrium state. If this plate was bigger, we could fit more electrons here, which means more electrons would be missing. So capacitance directly depends on the area, and it's the area of the matching part. So if you have a small one and a big one, it's the area of the smaller one. Also, the distance between the two plates matters, because the greater the distance, or the smaller the distance between the two plates, the more they attract each other, which pulls more charge around. So for a capacitor, a really large capacitor, you want large plates and a small distance between them. And then, if this is air, you know that air has an electric field breakdown value at 3 megavolts per meter, 3 million volts per meter. Please remember electric field, the equation, the electric field magnitude is potential difference divided by distance. So I'm going to use D here since that's the distance I'm using. And this is absolute value. So the closer they are together, the stronger the electric field I can get, so more charges. But they can't touch. If they touch, then these electrons are going to go back here. And we don't have a capacitor anymore. We just have a continuous current path. So we usually fill this area with a material called a dielectric. The most common dielectric to use to make capacitors is actually waxed paper. But when you fill it, one, the two plates don't touch. And if you use something really thin like waxed paper, they can get really close together, so a small d, but they're not touching, so we still have a capacitor. And the wax in the wax paper makes this breakdown strength go up. So it's easier to store more charge because we can exceed this value. And so different dielectrics have different dielectric constants, it's called. So the dielectric constant, and the symbol for that is the Greek letter kappa. So it looks like a capital K that I'm drawing in just the lower half, because this is actually a lowercase kappa. So the dielectric constant is different for different materials, and it's just a number. It could be 2, it could be 15, it could be 27. You'll see some examples in some of the problems you're going to do. So now, to build this capacitor, This is the definition of capacitance. The purpose of capacitance is to store charge for a particular battery voltage. But to build a parallel plate capacitor, we pick our dielectric. Epsilon naught shows back up, remember, 8.85 times 10 to the negative 12, and then times area divided by distance between the plates. So the bigger the area, the bigger the capacitance, the more charge it can hold. The closer together, the more capacitance, the more charge it can hold. The stronger the dielectric, the more capacitance, the more charge it can hold. Now, the unit for capacitance is the farad, abbreviated capital F. It's named after Faraday, who did a whole bunch of stuff in electricity and magnetism. So a farad is equal to the unit of charge is a coulomb, and the unit of potential is the volt. Most of the time a farad would be a really big capacitance, because if you have like 3 volts, then 3 farads would give you 3 coulombs. And you know, we don't often see coulombs of charge. So you'll often have millifarads, microfarads, even nanofarads, picofarads also exist. Now, all of that's well and good, but why would we want a capacitor? So here are some examples. After you charge a capacitor, potentially slowly because these wires do have resistance, there may be something else in the circuit. So after you charge the capacitor, if you connect it with a switch to a different path, you can discharge it very quickly, which means you can get a whole lot more current than was used to charge it from the original battery. And we'll talk about the limitations of batteries in the next unit. They actually have an internal resistance. So a discharge of a lot of current really quickly, we could use that in a camera flash. So that's one. And if you've ever noticed on a camera when you turn on the flash that it kind of whines a little bit and eventually the light comes on because you're ready to go, well, that whining is the charging, and the light comes on when it's fully charged. And then you hit the button to take the picture and it discharges through another circuit much faster, so you get a big bright flash of light. Another one is when you push a letter on the keyboard on the computer. Inside there, that's a parallel plate capacitor. When you push down, you're making D go down, which makes the capacitance goes up, which means if you have a constant voltage, which is how they work, you're storing more charge. So that's how the computer knows which key you pressed. You change the capacitance of that capacitor, so it changed the charge stored, so the more charge flowed into it, and it's hooked up to a particular line that knows you push the S as opposed to pushing the M key. And then a third one is the screen on your phone, or any touch screen. In that case, the 2 plates of the capacitor, your phone screen is one of the capacitor plates, and it's not charged at the moment, or maybe it only has a slight one. Your finger is the other half of the capacitor, because we are not great conductors, but we're okay conductors. So the screen responds to your finger and says, oh, hey, now there's a charge pulled over to this location, because that's where your finger is. So you must be trying to push this button, or swipe this way, or push this, connect these 2 colored things on Diamond Diaries or Candy Crush, like I spend too much time playing. But this is also why when you're wearing gloves, your phone touchscreen doesn't work. You can't get close enough to actually do the capacitance because you've got those gloves on. I actually have a special set of gloves. Unfortunately, I don't have them with me today, but my gloves came with a different color, like they're all gray, but the tip of this finger and this finger are black because it's got a little bit of metal in it. And so these 2 fingers, when I have my gloves on, I can actually use with my phone. But if I try with these fingers, nothing happens. But you've got to have that little bit of conductingness so that you can make a capacitor with your phone. Now, one more thing to talk about capacitors. If we are storing charge, we are also using energy. And capacitors are used in circuits to store energy. There are capacitors in just about every electrical circuit or electronic circuit that you've ever run into. So let's slow down a little bit charging this capacitor. So, oops, battery, delta V plus minus. So we have our first electron. It leaves here and it ends up over here. And I'm going to call that dq. And I'm just going to talk about adding electrons to this plate. So I've moved 1 electron on here. Well, now the battery says, hey, I can store more. So it takes another electron and moves it down here. So I have a second DQ. Of course, leaving a lack of electrons, so a positive charge up here. So the first charge, the first DQ, was easy. Nothing to push back on it or repel it. But the second one is just a little bit harder. Because yes, the battery's pushing it, but there's an electron here to prevent it from coming here. And then charges and charges and charges get more and more. So I want to remind you of the equation that delta U is Q times delta V. So I've got to turn this into an integral, because I've got to do a lot of charges one at a time, and I'm going to add them all up. So if I substitute for the potential, I'm going to go back up to my definition of capacitance. So if I move delta V to the answer side, then it's Q over C. So delta V is equal to Q over capacitance times dQ. So I already have some charge there. And now I'm going to integrate this charge, or I add together all these charge by integrating. So the integral of Q with respect to Q is Q squared. And then I have to divide by the new exponent. And then C was a constant, so I just pulled it over. So, I'm going to turn the page. The way this is usually written is with capital letters. So delta U from that derivation is Q squared over 2C. Well, delta V was equal to Q over C. So if I substitute, Q is equal to C delta V. So delta U is also C delta V squared over 2C. So C squared delta V squared over 2C. And so one of the C's cancels. So I have delta V squared times C. I don't like the way I'm writing that. Let's try again. All I have in the denominator is a 2, so I'm going to write 1/2 C delta V squared. And then the way it's actually usually first written in terms of definition is not including C at all. So again, if I go back to the one I got from the computer, or from the derivative, the integral, oh my goodness, delta U is this, C is Q over delta V. So delta U equals Q squared over 2 times Q delta V. So this is 1/2 Q squared times delta V over Q. And so one of the Q cancels, and I get 1/2 Q delta V. Okay, to summarize, delta U, I personally always remember, is 1/2 Q delta V. Then it's also Q squared over 2C, and it's 1/2 CV squared, delta V squared. So 3 different ways of writing it. For some reason, your formula chart only does 2 of them. It only does this one and this one. I don't know why it doesn't also include this one, but it does have the definition of capacitance on there, so you can always rearrange it. So depending on what you know in a problem, you'd find the energy stored on the capacitor from a charge in the battery voltage, charge stored in capacitance, or capacitance in voltage. Those are all fine. Now the last thing I want to point out is, remember, the basic equation was delta U is Q times delta V. This came from the definition of potential. Electric potential difference is defined as electric potential energy divided by the charge experiencing it. So this is all from an external source. The reason we end up with the 1/2 for a capacitor, so you'd only ever use this equation, this version of it, for a capacitor, is that this Q came about over time. There were a bunch of Q's, and they led to this potential difference across the capacitor, because essentially it transfers it from the battery. So that's why there's only half as much stored as a charge moving through a potential difference completely external to it if it all moved at the same time. But this being built up little by little and producing this potential difference is what leads to the 1/2 power. So I hope You notice a lot of similarities with the resistor stuff, but I'm not going to bring too many of those back in because there's some interesting differences. And we'll talk more about that in the next video. So, capacitance definition, building a parallel plate capacitor, and then energy storage in a capacitor. Those are the three main ideas.